Good morning. Today I want to talk about some various topics related to radioactivity as we close out Chapter 16. So we're going to focus on a couple of nuclear processes and then look at the effects of radiation and then some of the uses of radioactivity. So we're going to start with fusion. So in the previous section, we talked about nuclear fission, right, which was the splitting of the nuclei commonly used in nuclear energy and atomic weapons. Now, nuclear fusion, right, is the combining or the joining of two small nuclei into a heavier one. So we have nuclear fission, which is the splitting, and nuclear fusion, which is the combining of nuclei. So just like what we mentioned in fission, fusion emits tremendous amounts of energy. It is most commonly associated with the energy source that we have in the sun and many other stars. Right? And so tremendous amounts of energy emitted during the fusion process. It's also basis of what are known as hydrogen bombs or H-bombs. So when you see the term hydrogen bomb, it's actually a fusion weapon. Now, these fusion weapons actually use a fission explosion or a fission reaction to get started. Now, if we think about fusion, it produces, on estimate, about 10 times the energy per gram. Now, the reason for that, of course, is that we're using very lightweight nuclei, right? Whereas in fission, we're using very heavy nuclei, so the energy per gram of material is going to be lower. So when we're using these very light nuclei, we get 10 times the energy per gram of material. And we'll also see that the products that we make are less problematic, right? We don't have to worry about so much radioactive waste when we talk about the products. Now, the limitation, right? I mean, what we might be thinking at this point is that nuclear fusion, right? This is great, right? It's a great energy source, right? It doesn't generate nearly as many radioactive products, produces just as much energy as fission. Why not use it? Well, one of the biggest thing that we have to is that it requires immense input of energy to initiate the reaction, right? So this is why the fusion reaction at stars occurs at very high temperatures. Temperatures, that we associate with the sun, right? And why we need an actual fission reaction to initiate the fusion reaction in an H-bomb, right? It requires a tremendous amount of energy to initiate the reaction. And this has to do with overcoming the repulsion of the positive nuclei, right? We're asking two nuclei to come together. Well, they're going to repel each other. We have to overcome that repulsive energy. Now, if we look at a sample fusion reaction, this is similar to the one you used in an H-bomb on the surface of the sun, etc., where we have isotopes of hydrogen. We have tritium, which is an isotope which has a mass number of 3, and deuterium, which has a mass number of 2. If we smash these two nuclei together, right, collide these two nuclei together, the products are a helium nuclei, right, not terribly radioactive, right, not a radioactive isotope. It's an alpha particle, essentially. So we do have to worry about alpha particles, but not long-term actual radioactive nuclei, and a neutron. So these are the types of reaction we talk about when we talk about fusion. Now, in terms of using fusion as an energy source, we have tried it. We have built small-scale fusion reactors and spent quite a bit of money trying to work on fusion reactors, but At this point, because of the very high temperatures that are required to build it, we have to produce a plasma. You can see there's magnetic coils that will maintain the nuclei that are fusing during this reaction. But as of this point, the amount of energy that we've gotten out of a fusion reactor has been less than the amount of energy we've had to put in to get the reaction to occur. So because of the conditions required for fusion, it is not yet a viable energy source. There is still some research going on, but that research has declined over the last few years. And at this point, the fate of fusion as an energy source is quite unknown. Now, we're going to leave the world of fission and fusion here, and we're going to talk about another type of nuclear reaction, which is what we call transmutation. So nuclear transmutation is the combining of atoms of one element to transform them into a different atom by some sort of nuclear reaction. So essentially, all of these reactions involve collision of either two nuclei or colliding a nuclei with some subatomic particle like a neutron. So there's been lots of different transmutation, and this is typically how we've made some of these very heavy elements that we've talked about being discovered recently, some of these ones that do not exist naturally, right? And these are made by transmutation, by colliding these other nuclei in order to get these what we call artificial elements or man-made elements, right, that don't actually exist naturally. So these reactions are done, again, by accelerating high energy particles and smashing them into some sort of target nuclei. Now, these were originally done, some of the early ones were made to make oxygen-17, nitrogen-14 by using alpha particles, right? So they would take something like, if we want to think about a reaction, we take something like nitrogen-14 collided with an alpha particle, helium nuclei, and what you'd get out would be oxygen-17 and a hydrogen nuclei. And so this is an example of a transmutation, right? And we've made various other particles or various other nuclei by this method. Again, another early one was Marie Curie's daughter, Irene Curie, and her husband created phosphorus 30 by colliding alpha particles with an aluminum nuclei. And again, what we typically a lot of times hear today is to make these very large nuclei, some of these ones that we're talking about being discovered. An older example is californium-244, which was made by colliding uranium-238 with carbon-12 nuclei in a particle accelerator. Now, modern reactions of this are done in what are known as particle accelerators. And these particle accelerators come in a couple of different styles. We have linear accelerators and cyclotrons. Now, these are immense structures, right? There's some pictures in the book that these are not lab scale, right? These are huge structures that cover acres of land, right? Stanford has the most well-known linear accelerator. There's a picture in the book. And there's a few cyclotrons around the world. One of them is located at Fermi Lab outside of Chicago. And I've had a chance to visit that a couple times with members of our STEM club here. And it's really fascinating stuff to learn about. But the way these things operate on a sort of very basic level is they accelerate particles by alternating charge. Right? So they take these nuclei, right, these positively charged nuclei, and they accelerate them through either a linear accelerator or through a circular accelerator where it's going around in ever-increasing radii circles by alternating the charge. And in that way, these positive particles, they make where it's at positively charged, which repels it, and at the same time, the next area that it would enter is negatively charged, which pulls it along. Then they alternate the charge, and that becomes positive, and it repels it, and the next section becomes negative. And by this process, we just continually accelerate these particles by this push-pull idea. And so we can get very high-speed particles, approaching the speed of light in some of these accelerators. And then these particles would collide with some sort of nuclear target, and this is where we would get that reaction. And then we study the particles that come off of that, the products of that, and we see what we find, right? So we study the output of these collisions to see if we've made a different element, if we can discover something about the subatomic particles that are given off when these atoms hit a very target at a very high speed, etc. This is how they do a lot of work with things that you may have heard of, like quarks and other subatomic particles. Okay, so we got nuclear transmutation, the making of synthetic nuclei through the collision of other nuclei. So we can look at a couple pictures here where we look at a particle accelerator. So this is a linear accelerator. This is a Stanford linear accelerator. You can see the scale these are on. And essentially, you're going to have your particle here, and it's going to move through this tube, and we're going to alternate the voltage, so the sign at these various locations, and we're going to accelerate the particle through this tube, and it's going to smash into our target here. And of course, this is occurring in a vacuum, so we can get, high speeds here. Next, we got a linear accelerator, and then we have a cyclotron. So this is a close-up of the Fermi cyclotron. You can see the rings here of the cyclotron. And the difference here is we alternate the charge on the two halves of this. So the particles would start in the center, and they would then make their way in and out, going in and out of, being repelled by positive, attracted by negative. Then we'd switch, and it would just keep being pushed back and forth, push and pulled back and forth as it moves around the circle to the different sides of the circle until it reaches the outside, and it's very high speeds, and then collides with the target, giving us our transmutation reactions. Okay, so this is the last of our nuclear processes that I want to talk about. So we got fusion, and we got transmutation, and what I want to enter into the next few sections is talking about some of the other effects of radiation. So now we've talked about different reactions, but now I want to talk about, we have these radioactive materials. What are the effects of them, especially on biological life? Okay, so let's talk about the effects of radiation on biological life. Right? So the biggest thing to think about here is that when we talked about the ionizing effect of radiation, right? So where radiation does its damage is it ionizes molecules, right, in the living cells. And when those molecules are ionized, they then don't function properly. They function in ways that we don't want them to function, and that leads to cell mutations and other sort of effects within the body. Now, how do we get exposed to this radiation? Well, there's essentially two types of exposure. We have an acute exposure, right, which is a very high-level exposure over a short period of time, which can kill large numbers of cells. And this is what we might get from being close to a nuclear explosion, like a nuclear bomb, or an exposed core reactor like occurred at Chernobyl. And so it results in, very weakened immune system, lower ability to absorb nutrients, may result in death, if not immediate, short term. Typically that death, like in a lot of situations, comes from secondary effects from the radiation because of the lowered immune system and other issues that directly result. We're more prone to infection and other diseases, which ultimately a lot of times are the cause of death. Now, of course, we get longer-term effects, right? If the short-term effects don't kill us or, kill us in a short period of time, then we can get longer-term effects such as cancer, genetic effects that we can pass on. Now, these type of effects can also be caused by what we might call a low-level exposure, but over a prolonged period of time. So maybe you're not exposed to a high-level exposure over a short period of time, an acute exposure, which can lead to very quick death, but you're exposed to low doses over a long period of time, which you might think about as a chronic exposure. And some of the issues that we see here are increased risks of cell mutations, which lead to cancer, DNA damage, which can lead to genetic effects, whether those be birth defects or, genetic effects that damage the host, the person exposed. So cancer is probably the one that we think about the most, right? The DNA damage can cause cells to grow in an abnormal way, mutations to occur, and they can develop into cancerous tissues. Now, how much radiation can be exposed to? Well, it's more complicated than just saying, this much radiation will cause this and that and the other. It's a fairly difficult process to expose because different parts of the body respond to radiation exposures in different ways, right? And so, depends on if it's an isolated exposure to a specific part of the body, is it total body exposure, these kinds of things. So, if that exposure leads to damage to the reproductive cells, right, that's where we're likely to get genetic defects, right? If the sperm or the eggs in a female are damaged, that's where we get genetic effects. If other parts of the body, are exposed and damaged, then the effects are most likely going to be only to that host, the exposed person. Now, as with all things, it's difficult to get a direct cause and effect, right? We can say that, okay, this person was exposed to radiation, that may have led to damage to their reproductive cells, which can lead to birth defects, but we haven't been able to verify this in humans. We've studied it in animals, but, we have a fairly high confidence that this is a potential problem. It's just verifying this is not a trivial effect, right? We don't want to expose people to radiation, and so this is not something we're going to study by exposing people and seeing what it causes, you need cases to study. Now, measuring this, like I said, measuring this is a tricky business sometimes. So just to simply measure radiation, we can do that in a number of ways. Right? We typically measure by exposure, right? And so what we mean by exposure is what we call the number of decay events to which a person is exposed. So how many nuclear decays, which give off these forms of radiation, these alpha, beta, etc., gamma, has a person been exposed to? And we have the dosage, right? This is the actual energy that the person's body tissue has absorbed, right, from these nuclear exposures. Now, the basic unit of exposure is called the Curie, right? Named after, of course, Marie Curie. And the exposure, and the way this is measured, is 3.7 times 10 to the 10th. So about 37 billion events per second, right? So it doesn't matter whether it's alpha, beta, gamma, but 1 Curie of exposure is equivalent to 37 billion decay events per second. Now, another unit is what's called the Gray, and this is a measure of dose, right? So the Curie measures exposure, the Gray measures dose. And a Gray is equal to exposure of 1 joule per kilogram of body tissue. Right? So if you're exposed to 1 Gray of radiation, that would be the equivalent of being exposed to 1 joule of energy from a radiation event per kilogram of body tissue. Now, we have other units of exposure that you may be more familiar with and that are maybe more commonly observed. We have what's called the rad, right, which is a unit of 1/100th of a Gray, right? So this is, a Gray is a large amount of exposure. So a lot of times we'll measure in rads, right? Now, why not call it why not call it a centigray or something like that? I don't know. But the term that has been used is a rad. Now, how do we then translate these? So these are just units to measure radiation, right? Exposure. But we've already said that that radiation exposure can be more harmful or less harmful depending on where in the body it's exposed to, these different things. And so the most common or the typical unit of radiation exposure we use when we talk about human exposure is called the rem. And so the rem essentially takes the rad dose and combines it with something called the relative biological effectiveness, or the RBE. And that accounts for the difference in effect on different types of tissues in the body. So different types of tissues would be assigned an RBE factor, and then that would be, as you see here, combined with the dose in rads to give you the dose in REMs. So we take our rad dosage, multiply it by the RBE of that particular biological tissue, and that would give you your exposure or your dosage in REMs. Now, the average person is exposed to about 310 millirems per year. So, about 310, again, millirems. So, about, be equivalent to about 0.31 REMs. So about 1/3 of a REM is a particular average exposure per year. Right? So, but the effect of that, or what I want to get across, is we are typically not exposed to a whole lot of radiation over the course of the year, and this takes into account all the different kinds of exposure that an average person would be exposed to. And, if we look at a table, what I want to point out is to cause any of the sort of what we think about as the effects of radiation, it takes a much, much larger dose than what we can get on a natural basis, right? From things that we're commonly exposed to. So let's think about this table where we look at the effects of instantaneous. So these are acute exposures, right? These are exposures we're exposed at one time to this amount of radiation. So if we're exposed to a dose of 20 to 100 rems, right? So this is getting on boards of 1,000, close to 1,000 times, or excuse me, 100 times the normal dosage, right? The annual yearly dosage. So already many times more than what we would normally be exposed to. This can cause an increased cancer risk, right? Typically decreases white blood cell count, etc. Now, you start getting into up to 1,000 times the natural dosage. So remember, that would be about 300 rems, would be 1,000 times the natural dosage. Then we start to get things that we associate with people that are exposed to, in nuclear accidents like Chernobyl, or the bombs at Hiroshima and Nagasaki, right? Radiation sickness, vomiting, diarrhea, skin issues, and of course, long-term cancer risk. Now, we start getting into extremely large exposures. So, multiple thousands of times the normal exposure. Then we start leading into, fairly certain death, whether it's over, a couple month period or instantaneously, essentially. But the take home here is that you have to be exposed to much more than what you would be exposed to on a natural living basis to have any of these issues from radiation exposure. Now, when we think about natural radiation exposure, or sort of the normal radiation exposure of the average person, what are we talking about? Well, if we look at some of these sources, you can see that it comes from all sorts of places. And if you notice, these are all in millirems for the most part. So things like flying in an airplane, right, for a long period of time can give you a very small exposure. A lot of the exposure we get to, about a tenth of our annual exposure is from cosmic radiation, right? Radiation from space, right, that we can't really do much about. Another tenth of that exposure is from terrestrial radiation, radiation from radioactive isotopes that are just naturally decaying in the ground. And about another 10% is from natural radioactive nuclei in the body, right? We consume minerals and some of these isotopes, even of things like potassium and these other sort of things that we think about, some of the isotopes are radioactive, right? They're in very small natural abundances, and we get small amounts of radiation from these sort of natural exposures within the body. Now, a fairly significant exposure comes from our exposure to radon gas, right? So radon gas is a byproduct of uranium decay, right? Radon is also a radioactive isotope. It's part of the decay process of natural uranium, usually. And it's a gas, so it seeps out of the ground. And this is, in this part of the country, right, we worry about getting radon exposure in our basements because we have fairly large amounts of radon being produced in this part of the country. So these are the quote ones we get from nature. Right? Now, the other exposures that go into the sort of annual dosage come from man-made sources, but sources that we're normally exposed to. Things like medical procedures, like x-rays, right? So if you have any of these things over the course of a year, you're going to get these kinds of exposures. So whether it's a chest x-ray or dental x-rays, right, can give you mammograms for females out there. These other less common procedures like barium enemas or other sort of radiological exposures, whether it's into an upper GI or an heart scan or a CT scan of different parts of the body, right, can give us increasing dosages. So this is where you start having many of these procedures, right, and you start easily exceeding sort of the normal 300 millirems that an average person would be exposed to. So that 300 is mostly going to come from the natural, and then a little bit for the average person, right? They're getting maybe one of these per year, right? Not many of these. Maybe we get dental x-rays every year or every couple of years. Maybe for female, we have a mammogram every year. Maybe, we have to have an x-ray for something, right? And you're going to get maybe one of these exposures per year on average. And then other man-made sources of radiation come from things like building materials. So concrete, bricks, right? Cement, right? These things all have, radioactive isotopes in them, and they give off small amounts of radiation, right? And we're talking, fractions of a millirem or a couple millirem. Now, I will point out this last one. This is by far the largest potential exposure and the most avoidable exposure, and that is if you smoke. Now, this maybe is an elevated number, but you could even cut that in half and you'd see the exposure, right? Smoking provides about 16,000 millirems if you were to do 30 cigarettes per day. You cut that in half and you're still at 800 millirems, right? Over twice the natural exposure from smoking 15 cigarettes a day. So this is kind of where we get that radiation from. Now, in the last part of the chapter, I want to talk about some of the uses of radiation, right, or of radioactive isotopes. So we've talked about the exposure and the damage, and that's usually from inadvertent exposure or exposures that we don't have a lot of control over or that we just kind of have to live with, right? Now, let's talk about some of the good things, right, that radiation can be used for. So the bulk of these uses of radiation or radioactive isotopes are going to be medical, right? So we're going to talk about a few of these medical uses that are used for both diagnostics, right, to diagnose things, and for treatment. So a lot of these involve the use of what we call radio tracers. So this is where we'll attach a radioactive nuclei, a nuclide, right, to some compound and that we normally would have in the body, and then that compound would be taken to the part of the body that we're interested in studying, and we would measure the radiation that's given off, right? We can measure the use by measuring the radiation that's given off or using that radiation that's giving off as an imaging tool, right? We can measure that radiation, and through computers, we can take that energy signal, right, that radiation that's given off, and we can use it to create an image. And so the radio tracer would be chosen and attached to the compound of interest because it's used by some particular organ on the body, right? And we can then measure, quote, the tagged isotope. So these are the molecules of that particular compound that have the radioactive isotope upon it, by using things like Geiger counters or other more, high-tech technology, if you will. So let's look at some of these diagnostic tools. So the first one is what's called a bone scan, right? So this is, we've used a radio tracer. In this case, the radio tracer is technetium-99. And it can be absorbed into the bones. And then we can then image the bones, and we can see different parts and look for signals where maybe a particular, irregularities or etc. We can locate tumors, etc. by scanning different areas of the bones, because the idea is that cancerous tumors are going to have different uptakes of these particular molecules that we're measuring, and so we can measure where this material is being used the most, and that's going to give a different type of energy signal as opposed to other parts of the bones where they're not. So you can see the kind of image you might get out of something like a bone scan. Now, these can be used to target various organs. Now, using these various organs, we're going to use different nuclei that are going to be absorbed by different parts of the body. So, for example, we mentioned technetium-99 being used by the bones. We can use iodine-131, right, to image the thyroid. The thyroid naturally uses iodine. Right? Iron is useful for blood and areas of the body where blood, it can be particularly useful as a tool to study. You can use thallium for heart scans. Fluorine is used for brain scans, or to scan the brains. That fluorine is typically is attached to glucose, right, which is heavily utilized in the brain. And so we can measure the uptake of glucose in different areas of the brain and measure the radioactive emission from the radioactive isotopes of fluorine that can be incorporated into glucose. And, phosphorus can be used in various organs. Now, one of the key things to look at here is the half-lives of these various radioactive isotopes that have been chosen, right, are all fairly short, right? So they're going to be out of the body within, days or weeks, at least to a large portion, right? The longest one is the iron, and that takes 45-day half-life, so it's going to take, a few months, maybe up to, a year to really work its way through the body. But most of these other ones are in hours, right? Or much shorter periods of times. And so over the course of days or months, they're going to be eliminated from the body. Now, I'm going to talk about just one or two specific techniques. And I talked about the use of fluorine-18 to utilize the brain. The technique is what we call a PET scan, or positron emission tomography. And as I mentioned before, right, fluorine-18 in that chart is a positron emitter, so that's where the name comes from, right? Positron emission tomography. And so we've incorporated fluorine-18 into glucose, and then we can measure the glucose uptake in different parts of the brain in areas of higher uptake. Could be targeted for maybe where there's an issue going on, or we can monitor areas where there's less uptake, more uptake, whatever we might be looking at, but we can do what we refer to as a brain scan, right, or a PET scan to look at the glucose uptake in different parts of the brain during different, maybe it's stress responses or episodes or seizures or whatever, all sorts of things that people can look at here. Now, diagnostic is one thing, right? Radiation can also be used as a medical therapy or a treatment, right? This is most commonly associated with treatment of cancer, right? Using gamma radiation. One of the common isotopes that are used as the source of gamma radiation is cobalt-60. And so in this we have external, right? We don't use radio tracers, well, at least not that radio tracers can't be used to treat cancer, but when we think about radiation therapy, right, we're talking about external exposure, where we target gamma radiation exposure to the area where we have tumors, right? Now, cancer cells are more prone or more sensitive to radiation than healthy cells. And so we can hopefully use the radiation to kill the cancer cells without significant damage to healthy cells. Now, there's always going to be some sort of collateral damage, but as technology gets better, as targeting gets better, as we understand more about how much dosage we really need, right? All of this stuff can be reduced to as minimal as possible. So these are large exposures, right? So, this is why we see people that go through radiation therapy having other side effects, right? Because they're essentially getting radiation sickness to some extent, right? Loss of hair, nausea, vomiting, right? Because we're seeing about 100 rem exposure, right? And so if you look back at that table, right, 100 rem exposure, right, is sort of the low threshold for that kind of radiation sickness that we think about. Now, we're going to close out this by talking about some other general uses of radiation, of where we might be useful, and in the non-medical field. Right? Now, one that maybe you don't know, but everybody's exposed to, right, is we use it in smoke detectors, right? That uses americium-241, right? And so it's used as a circuit, as part of the circuit in a smoke detector. And so normally, right, this is an emitter, and so it emits the radiation. That emitted radiation is absorbed by a detector, the target, and the circuit runs. The smoke will block the ionized air, and so you break the circuit, you set off the smoke detector. So the americium, we all have small bits of typically the americium-241 sitting around our house in our smoke detectors. It's used to sterilize insect populations, right? To control things like mosquitoes and other kinds of insects. It's used to sterilize food, kill bacteria. Like you see the pictures of strawberries. So oftentimes fruits and vegetables and meat are exposed to radiation to kill bacteria. Now, this is where I have to remind everybody that exposure to radiation does not make something radioactive, right? The only way that strawberry is radioactive is if you actually inject it with radioactive material, and so it actually contains radioactive isotopes. So exposure to radiation doesn't make something radioactive. So even if a person is exposed to, gamma radiation, that person doesn't become radioactive, right? And same thing with a strawberry, right? So it's a safe way, a very easy way to sterilize things, right? It's used, again, to sterilize fruits and vegetables and meat, and more things like healthcare products like makeups, contact solution, right? Can be used as a method to where we commonly see bacterial growth. So it's used to sterilize a lot of things to get rid of bacteria. And then in research, right, we use, similar to what we talked about with using radioactive tagging in medical treatments, we can use radioactive tracers to measure the progress of a reaction, right? We can follow the path of a particular radioactive molecule, right? If we've incorporated a radioactive isotope, we can measure the radiation being given off. We can follow that radiation through the reaction process and sort of measure how fast it's going, where it's ending up, these kinds of things. So all sorts of different uses for radiation or radioactive isotopes in all sorts of areas of life. All right, so that's going to bring to a close our look at radiation and radioactivity and all different aspects